Hello and welcome to another episode of Enough with the Science. Joe, I have a challenge for you.
Oh no, here we go. The starter question for one.
In words of one syllable or less, explain what we do here.
Well, basically, you're very welcome along to Enough with the Science. And myself and Senan, it's actually Senan discusses science topics and I try and understand them by peppering them with questions.
Do you understand what a syllable is?
No. That's next week's. I thought that was next week's show.
Anyway, I thought this week we'd start with a song.
Okay, off you go.
You know,
yes.
I'm a world famous singer, and you know, we really should let this podcast benefit from my skills more often.
I'm leaving. I'm not doing this.
Catch a falling star and put it in your pocket.
This is what we needed. This is what we were missing. This is what is going to get us up the podcast charts immediately. I could just see it going, what were you missing of all of those, like the first series, of the last 6 episodes of the second series? What were you missing? Senan singing. Yeah. That was it.
Senan singing songs that are copyrighted and are going to get us pulled off every published medium. Anyway, imagine if you could catch a star and put it in your pocket and do something useful with it.
But burn a hole in your trousers, burn a hole in your pocket. I would imagine a star would.
Potentially, I suppose. You need an awfully big pocket too. Anyway, that's kind of the subject this week. We are talking about fusion, which of course is the engine that drives the stars.
Very good. And this is possibly the panacea for all our problems in the world.
Panacea? That's an Italian bread, is it?
I thought it was meat. It's meat? Panacea? Panna cotta? Is it panacea?
Panacea?
Panacea.
Oh, yeah.
Panacea for all man's ills.
Yeah. Right. It's the engine that drives the stars. Why are we interested in it? Well, it's kind of seen as the holy grail of energy production. So we can... The fuel that's required for it is very abundant. So it means if we can get this thing to work, it's very, very complicated. And although we've got it working in laboratories, making it into commercial power generation is a whole different.
So essentially, it's like nuclear power, but without the negative connotations.
Yeah, and also with a very cheap, abundant supply of fuel. Like we've loads of the fuel that you require, and it's very easy got and cheap and all that. So existing nuclear power, and indeed nuclear weapons for that matter, is nuclear fission, where we are taking heavy elements like uranium and plutonium and we are splitting them up and making them into smaller elements.
We're breaking stuff.
We're breaking them apart and we get some energy out. Unfortunately, we also get an absolute pile of very dangerous radiation, and one of the worst aspects of it is that if you're not very careful, the reaction becomes a runaway meltdown. In other words, the reaction just gets hotter and worse and worse and worse and just melts everything in sight and releases huge amounts of radiation into the environment. So it's a real tricky one to control. And although we haven't had many accidents, like we have had a couple, like Chernobyl, Fukushima, 3 Mile Island, and all of them had very serious implications for the area nearby. So, you know, it's...
And yet we still rely on it.
We do, because it's our apart from burning fossil fuels, which of course are polluting the planet and causing greenhouse gases and so on, it's one of the few other viable methods of producing electricity. Obviously we have wind and solar, those are coming on screen and we've got more and more of them all the time, but still it is one of the most popular ones because it does generate a lot of energy. So what is it about? What is fusion anyway? Essentially, unlike, it's kind of the opposite of fission. So fission, I said, we're taking heavy elements. We're taking fish from the sea. We're taking heavy elements and we're splitting them apart until they become lighter elements. With fusion, we're taking very light elements and we're squashing them together until they fuse into a heavier element.
Okay.
And when that happens, we get some energy out that we can use. It's interesting at the kind of atomic level how difficult it is to make that happen. So we're essentially bringing the nucleus, 2 different nucleuses, or nuclei is the correct plural for nucleus. We're taking 2 of them and we're squashing them together until they make a new nucleus of a different kind.
You make that sound so simple.
The thing about nuclei, is that they have protons in them, and protons have a positive charge. So if you get 2 things that have the same charge, like 2 things that have a positive charge, they repel each other. They don't want to come together, they push each other apart. So what you've got to overcome that somehow, because there's this other force then which exists inside the nucleus called the strong nuclear force. It's quite a strong glue that holds all the components of the nucleus together. But it only operates over really, really small, incredibly tiny distances. So if you want two nucleus to be pulled together and fused, you need to get them right beside each other so that the strong nuclear force can take over. So imagine it's a bit like imagine you have a couple of magnets. Now I'm going to give this is an analogy before I get slaughtered by the boffins that are listening to us. Magnetism is not directly involved in fusion. I'm only using it as an analogy. Say you have two magnets, and you point the north end of each magnet towards each other.
Positive.
And you start pushing them. No, that's electrical. Positive is electrical, and magnetism is north and south.
Oh,
yeah.
Okay, there we go. So you can't say a magnet has a positive and a negative. No,
we call it north and south. Yeah, because of the planet.
There you go with the we again. You and the others in the scientific community.
Exactly. Yes, and every textbook that was ever written about magnetism too.
Okay. See, I didn't know that. I thought you had a positive end of a magnet.
There you are. Anyway, take two magnets, point the north end of each magnet at each other, start to push them together, and you'll immediately feel them pushing apart. Let them go, they'll spring apart, right? Imagine then you took a bit of Velcro and you glued it onto the ends of those magnets, the north end of each magnet. And then you did the same thing. You kept pushing and pushing and pushing. You can feel them pushing apart until eventually the Velcro connects and they hook together and they're stuck together. So the Velcro
that is the strong nuclear force.
Yeah, the Velcro has overcome the magnetic repulsion. That's kind of an analogy for what's happening here with fusion. You've got the positive charge of the protons pushing them apart, but if you can push them close enough together, the strong nuclear force takes over and glues them together, right?
That's a very good analogy, Shannon.
Yeah.
Even I understood. I'm following this. I'm up there now. Strong nuclear force.
You are a nuclear scientist.
Like 10 minutes ago, strong nuclear force. Like what?
Don't get me started on the weak nuclear force, because
that's next week.
That's a thing too. Anyway, that's grand. But we're only interested in this whole fusion stuff because we want to get some energy out, right? So what happens? Where does the energy come from? Turns out there's a bit of weight left over, or a bit of mass. Mass and weight are not exactly the same thing, but as far as we're concerned here on Earth, they might as well be, right? So if you weigh, say you take two hydrogen nuclei and you weigh them, and then you somehow fuse them together and you end up with a helium nucleus as a result, and you weigh that, it's a bit lighter than the two you started with. There's some bit of weight missing. And effectively that missing weight gets converted into energy and released as energy. We need to go back to our old friend Einstein, who taught us all about this stuff.
We're going to have to get a bust of him in here for this room. A bust of Einstein so we can gaze disapprovingly at us.
Yeah, it's Einstein or bust. Just about everybody's heard of E is equal to mc squared, that famous equation that is Einstein came up with, that declares that energy and mass are interchangeable. So the E is energy, the M is mass, C is the speed of light, which is an absolutely huge number. And if you take a piece of mass, you weigh it, you multiply that number by the speed of light, and then you square the answer, that's the amount of energy you're going to get out. So that's essentially what Einstein was talking about. It's an enormous amount of energy. So imagine 1 gram of hydrogen. So hydrogen is a gas, but a gram is a very tiny amount. There's 1,000 grams in a kilogram, and a kilogram of anything you can hold in your hand.
Really?
Yeah.
I think that's enough for this show.
Did you never get that kilo thing before?
Actually, can I just go back for a second? I thought E equals mc squared. I thought that was energy equals mass multiplied by the speed of light squared.
Yes, that's what I said. But that's what I was trying to say anyway.
No, but that it's mass by the speed of light squared, not mass by the speed of light squared.
I see what you mean. Yeah, good point. Yeah, good point.
No,
you might be right. I might be wrong.
Okay.
The roles are switching here. The roles are reversing.
That's my job. Keep you honest.
You could be right. That's it. My reputation is ruined.
Look, you sang that 5 minutes
my
ago.
Reputation was ruined already. Fair enough. Yeah, I can say any crap now. If just to explain or help people visualize what this equation really means. If you took 1 gram of hydrogen and you were somehow, it's not anything we know anything about how to do this, but if you were somehow able to convert that entire mass, that entire 1 gram of hydrogen into all energy, it's enough energy to boil 100 Olympic swimming pools. It's like a phenomenal, that's out of a gram of hydrogen.
Why would you want to do that?
Well, I'd like to get all that energy if I could.
No, but I mean, boil the swimming pools. I mean, like, where's the happiness there? I mean, facetious. Pray continue.
So now fusion is not converting all of the hydrogen to energy. There's just a little bit of the hydrogen's mass left over, and that bit is getting converted to energy, and that's why we're interested, because we want to get that energy and use it for something. What's the difference, right, between fission and fusion? As I said, fusion, very light elements being stuck together to make heavier ones. Fission, heavier ones being pulled apart to make things. The waste products are probably a big part of the difference. Like fission produces really long-lived radioactive waste. It takes thousands of years for the radiation to die down from the waste products that come out of fission reactors. Fusion, there's a few waste products. Helium, which is harmless, right? You're creating new helium. The walls of the chamber where the reaction are taking place get made a bit radioactive by the neutrons.
Yeah, just a smidgen.
It's only a bit in comparison to like what's coming out of a fission reactor.
Yeah.
Like, okay, yes, they are radioactive, but it only takes decades for that radioactivity to dry down, not the millennia that would take the other stuff. One of the fuels we use is a flavor of hydrogen called tritium. That is radioactive and needs to be handled carefully, but it's not. We're not talking about plutonium or uranium here. It's not like majorly radioactive. And then there's neutrons streaming out of the reaction, and those have radiation associated with them. So you need to have some shielding. But again, it's far less than a traditional nuclear reactor.
And just in terms of the amount of energy that is released from fusion and the amount of energy that's released from fission,
yeah,
is it sort of the same ballpark for the amount of stuff you put in, that the amount of energy you get out?
I don't know the answer to that question.
Could you not just lie? Okay, no, it occurred to me there. I see why fusion is the way to go.
Yeah. I mean, fusion is just a whole easier thing to like. With fission, the hard part is stopping the reaction from running away from you, from getting more and more intense and melting everything in sight. Right. So that's like, once you start the reaction with fission, it's just going to keep going unless you step in and stop it by putting control rods into the middle of it to stop the reaction, right? With fusion, it's the opposite. The hard part is keeping the reaction going. Like, it's hard to start, and once you have it started, it stops awfully easily. So if the equipment in the reactor was to fail, the fusion reaction would just stop. Whereas that's not the case with the fission reaction. If the cooling system of a fission reactor fails, run. Very fast.
So fission essentially is kind of like a forest fire, whereas fusion is like a wood burning stove.
Yeah, that works.
I spent seconds coming up with that.
So the history of all this, right? How did we find out that fusion was going on in stars or in the sun, which is our nearest star? 120 years ago, the early 1900s, nobody really understood. They knew the stars produced light and heat, but they didn't understand what the fuel was, what the mechanism that was going on in the stars was. So they were able to calculate from observations roughly what the size and weight of the sun is. And they were saying, right, I wonder if it's coal, how long would that much coal burn for? If it's oil, how long would that much oil burn for?
They kind of ruled out wood pretty much straight away.
They possibly did, yeah. Anyway, they worked out that if it was like a hydrocarbon like oil or coal, there would only be enough fuel in the mass of the sun for it to burn for a few thousand years. But yet they knew from geology on Earth that the solar system is billions of years old. So clearly the sun had been burning for a lot longer than that couple of thousand years that coal or oil would have allowed it to burn for. There was a guy called Arthur Eddington in the 1920s who had this brainwave that he said, I wonder if hydrogen can be converted into helium and if that makes some leftover energy. So he actually came up with the whole mechanism, or at least, he had the ideas that ended up with us understanding the mechanism for
what he was doing at the time. That's a hell of a brainwave.
A hell of a brainwave. Yeah, I'd love to know what he was at. Yeah, wouldn't it be great if you could get in your time machine and go back and observe these light bulb moments that took place years ago with scientists?
Is that what you would do in the time machine?
That is what I would do. I know you would go forward and get the lotto numbers. The world isn't all about money. Anyway, later on then, there was a breakthrough with a guy called Francis Aston. He developed a gizmo called a mass spectrometer. It sounds complicated. It's a weighing scales for atoms. So
it's either very big or very, very small. You need a microscope to see it. Just the weighing scale.
Maybe it's both big and small at the same time. Anyway, he weighed. So it turns out that for fusion from hydrogen into helium, you actually need 4 hydrogen atoms because the hydrogen likes to hang out in pairs. So hydrogen would normally be H2, and so you need to fuse them together. You need 2 sets of that. So that's a total of 4 hydrogen atoms, and he was able to weigh those 4 with his mass spectrometer, and then weighed the resulting helium, and he realized, oh, it's lighter, something's missing here. And the obvious conclusion to him anyway was that the missing mass was being converted into energy.
So he actually did this. He made.
Well, no, he weighed
He
weighed hydrogen and he weighed
helium. Okay. Yeah, he didn't actually. Okay,
no, he didn't. He didn't do fusion. No.
Yeah.
So then, fast forward a few years, 1939, a scientist called Hans Bethe. He was a mathematician, so he was a theoretical guy, not an experimental guy, and he figured out the mathematics.
So he didn't really exist. This is someone you've invented to explain this concept.
Yeah,
okay, he's theoretical.
He was a mathematical matrix, not a person. Anyway, he worked out the sequence of events mathematically that happens to allow hydrogen get fused into helium, and along the way he figured out that there was 2 protons being released and converted into neutrons, which is going to be very important later, as we'll find out.
That's the cliffhanger. This is the cliffhanger bit.
The neutron.
What about the neutrons?
The neutron cliffhanger, yes. Yeah.
Protons changed to neutrons. What happened then?
So, the sun obviously is the poster boy for fusion. Why not just copy the way the sun does things? Why can't we do fusion the way the sun? We can't. Spoiler, we can't do it the way the sun does it. So the sun has a couple of tools at its disposal that we cannot hope to ever have here on Earth. Number one, it's so enormous that its gravity is mind-boggling, and all of the material in the middle of the sun is under incredible pressure from that gravity, a level of pressure that we could never recreate here on Earth. And as a result of it being squashed together, it's also incredibly hot. So temperatures again that we couldn't possibly achieve here on Earth. So the sun is doing what's called bare proton to proton fusion, and that is only possible at those temperatures and pressures. So we can't do it the way the sun does it because we just don't have the equipment to create that stuff, and we don't really want to set the Earth on fire by doing that either.
That's the first time you've admitted that. I thought you'd set the Earth on fire on a whim.
Yeah. I'll leave that up to the volcanoes. Instead, some boffin on here on Earth has figured out that 2 isotopes of hydrogen can be fused together easier than just bare protons. What's an isotope? It's like a different flavor of an element. So essentially it means extra neutrons in the nucleus. So deuterium and tritium, they are both still hydrogen, but they're like 2 different flavors of hydrogen because they have some extra neutrons in them. So we've discovered that it's possible to fuse deuterium and tritium at lower temperatures than you would have to do the proton to proton fusion that's going on in the sun, and also slightly lower pressures. Mind you, lower temperatures means 100 million degrees. It's still damn hot.
That is toasty.
So yeah, it's extreme. We need that temperature because we actually have to strip the electrons off the atoms or into what's called a plasma. If the electrons are still present going around the atoms, it'll prevent the fusion from taking place. So we need to strip the electrons off, and we also need to accelerate the speed at which those nuclei are zipping around. And that's why we need such incredible temperatures and pressures. So a plasma, by the way, is what's known as the 4th state of matter. It's this soup of nuclei that are zipping around without their electrons. And
right.
it's a real hot, energy-dense state of matter. So you need the temperature, you need density. In other words, you need to have these things squashed tightly together because that increases the chances that they collide with each other. And you also need confinement time. What does that mean? You need to keep that bunch of hot, dense stuff confined together in a tight space for long enough that the reaction becomes self-sustaining. So you get the reaction started, and if you allow these things to spread out, it just peters out again. So you need to keep stuff together long enough that the reaction becomes self-sustaining, and then you get extra energy out as a result of that. So, and the confinement thing is like a real challenge because
it's 100 million degrees.
100 million degrees. There is absolutely no material known to man that can survive contact with 100 million degrees.
Kryptonite. Is it kryptonite?
That was the thing that was Superman's nemesis, wasn't it? Kryptonite. I don't know. Did they cover the temperature profile of kryptonite? But
sure
I
we
do
can
know
find it.
we saw it in a very icy environment in one of the movies. So I'm thinking to myself, maybe it needs to be cold, not hot. Anyway, so there's two kind of main approaches to trying to confine this bloody plasma that's at 100 million degrees, and you basically neither of them involve using a physical material because there is no physical material that can do it. So magnetic confinement is probably, I think, the leading contender, and it takes advantage of the fact that the nuclei, which have protons in them, have a positive charge because those protons are there. That means that a magnetic field can steer them. A magnetic field can cause them to flow or bend in a particular direction. And we can build a containment donut shape, or what was it, somebody else, you said it was like a swim ring. Yeah, or imagine that shape. It's the Russians have a lovely word for it called a tokamak, which is an acronym of Russian words, I think.
For donut.
Yeah.
It's a Russian word for donut.
Anyway, you can then build that structure and put magnets into the walls of it in a special arrangement that will steer the plasma around and around and around without touching the walls.
So the magnets repel the plasma from all sides of the walls,
yes,
essentially, and keep it in empty space
in the middle. Yeah. Not in the hole in the donut.
Yeah,
but in the ring. It's flying around in the ring. And there's the magnets maintain a gap between the plasma and the walls of the chamber, because if it touches the walls of the chamber at all, it'll just melt them. So that's really what magnetic containment is all about.
Have they done this?
They have, but it's kind of experimentally for brief periods. Getting the reaction to last for a long period of time is difficult, and there's other difficulties that I'll come to. But yes, they have done it in a laboratory setting.
Like they have done it like at kids' school or a...
Well, as I said earlier, it mightn't be the end of the world because the reaction is so hard to start and to keep going that it's not going to run away. But the other, we'll come back to the magnetic one in more detail later because it is the leading one, I think. The other one, just briefly, I'll talk about, has been done in the US, called inertial confinement. This is like something out of Star Wars. This thing is like the Death Star. What they did was they got a tiny pellet of fuel the size of a peppercorn, right? And they got literally hundreds of lasers.
I just had an image of them doing with turf. That's where all the turf goes. You just need a peppercorn of turf and drop it into this.
So, and they literally have hundreds of lasers all pointing inwards in this circular spherical chamber at this point in the center. So all these lasers are aimed, literally hundreds, so that there is laser beams coming in. There's no gaps. There's laser beams coming in from every angle, up, down, bottom, left, right, top, you name it. And they all fire in perfect synchronization when the peppercorn of fuel is in the middle. And the amount of heat and force that they deliver heats it up to the required 100 million degrees and applies confinement, the force inward, confines it briefly. And then the reaction starts, and the reaction is in such a tight confined space that it further confines itself. So it's the inertia of the reaction is kind of confining it in that tight space inside the peppercorn for a brief moment. But it's enough to get some extra energy out. So the reaction, unlike in the tokamak one, the magnetic one we spoke about a moment ago, it's a continuous reaction. It's going all the time. This one is different. It's a series of very short-lived reactions, pulses, basically. Many of them every second. So you've got, of course, each time you fire the lasers, the pellet is destroyed. So you've got to drop in another pellet and another pellet and another pellet. It's all got to be timed exquisitely down to the millisecond.
That sounds mad.
It's bonkers. And the other thing is the lasers have to be extremely high power ones. The infrastructure required to drive those lasers is enormous. There's a huge amount of backroom equipment. This
is James Bond Moonraker.
Yeah, unreal. Yeah, this is like James Bond villain stuff. They did get it to work though, and they did prove that more energy came out than went in. So, but making it commercially viable, I think, is a huge leap.
How did they collect the energy?
We'll get onto the neutrons. So with these fusion reactions, neutrons are streaming out of them because there's extra neutrons being made by a couple of leftover protons, right? So there's a continuous deluge of neutrons streaming out in all directions. Remember, neutrons are not... We'll go back to the magnetic example because it's a bit easier to talk about. Neutrons are not... don't have a charge. They're not positive, they're not negative, they're neutral, hence neutron. So they ignore the magnetic fields. They just blast straight through the magnetic field. They don't care.
And are they dangerous? Are neutrons dangerous?
Well, yeah, they do carry some radiation. Yeah, there is some radiation. Now, look, you're not talking about uranium or plutonium here, but yeah, there is some.
I love the way you just less that. Yeah. As soon as you say anything radiation, there's no small level.
There is, for God's sake. Look at the difference in, say you go and lie out in your garden on a cloudless night when the moon is full moon in the sky, bright light is streaming down off that moon onto you. And then you lie out the following day in the middle of the day when the sun is shining. I bet you there's a difference in how you'll feel in terms of temperature. You're going to feel a lot warmer during the day than you are, even though there's radiation coming from both of those things. The point I'm trying to make is, yes, there is a difference between a lot of radiation and a little.
I know, but like, okay, in those things, like the radiation coming from the sun and bouncing off the moon, okay. But neutrons streaming at you, I imagine, is not somewhere you want to be.
No, you don't. No, but like you can build shielding that'll,
lead stuff. So like
strangely enough, lithium. But we'll come to that in a minute.
Okay.
So how do you actually get energy out of that situation? The walls of the chamber, they call it an energy blanket, which is a weird name, but basically the walls of the chamber have a honeycomb of pipes in them that water is flowing through. The neutrons that are flying out of the reaction are coming out ridiculously fast. And their kinetic energy, when they strike that material, the blanket, the walls, basically, of the chamber, the force of that collision imparts heat. So the kinetic energy gets converted to heat energy, boils the water in the pipes, and the steam is used to drive a turbine that generates electricity. So that's basically how we get energy out. I mean, you would have to do something similar with the laser thingy I spoke about a minute ago, but it's much more complicated because you've got all these bloody lasers in the way. So trying to get energy out, usable energy out of the laser version.
You have to direct it,
yeah,
like into a pipe or a.
Yeah, I don't know. Like they have managed to get energy out in the laboratory setting, but I don't know how they do it commercially viable. Anyway, so the next thing is what happens. What else are those neutrons good for apart from heating up water? Now the interesting thing is if you have some lithium. So lithium is a fairly common element. There's plenty of it on the earth. We use it in our batteries for our laptops and phones and so on. If you make some of the walls of the chamber out of lithium, when the neutrons hit that lithium, they actually convert some of it into tritium, which is one of the fuels we need. So essentially it's making its own fuel, or at least there's two fuels, deuterium and tritium. Deuterium is really common. It's in seawater. We've no shortage of deuterium, but there's not that much naturally occurring tritium. So we need a little bit of the naturally occurring stuff to get the reaction started. But once the reaction starts running, the neutrons blasting into the lithium in the walls of the chamber is actually converting it to tritium, and that's fuel. So
the fuel goes back in, so it's self-replicating.
It's making its own fuel as it goes along. Yeah, it's and that's one of the really cool things about it. And you don't need to use a whole lot. I mean, it's estimated that a commercially viable power generation plant, roughly the same amount of power as a nuclear reactor might produce, in a current power plant, that you would use about one swimming pool full of seawater and about the amount of lithium that would make batteries for 50 electric cars. So, and that's like a huge amount of power being generated. Compare that to a comparable coal-powered plant. You'd be talking about millions of tons of coal being used every year. So, it's very fuel efficient, and the fuel is not expensive or difficult to obtain. So, but there are other challenges. For example, the fusion plasma doesn't flow smoothly, right? So it's a turbulent flow. As it's zooming around inside in the donut, it's turbulent. There's waves and blobs and other, non-smooth things occurring in it. And that brings the risk of it bashing into the chamber walls and destroying the chamber, because it'll melt it immediately, like a half a second of contact with the chamber walls and the chamber is gone, basically.
And maybe you don't know this, but what is so the plasma is flowing around a donut inside a donut, essentially.
Yeah.
But what is there? Is it a vacuum? Is it a vacuum?
Well, I mean, the plasma is, remember, hydrogen and helium nuclei. Mm-hmm. So it's not a vacuum in that regard. Yeah, but there's nothing else in there.
Yeah, it's 100 million degrees. I'm just wondering, whatever else is in there is gone.
Like drop in your marshmallows for a second, and you'd be in business. But no, I mean, it's just the hydrogen and helium.
Okay.
and an awful lot of neutrons. So there's some challenges that neutron. So the plasma thing, the instability in the flow of the plasma is a big challenge. They're doing a lot of work on trying to finesse the magnetic field that it will react to, like if a wave appears in the plasma flow, that the magnetic field can synchronize with that wave and push it back in, that kind of thing. They're using AI to do a lot of modeling about the fluid dynamics of the plasma and stuff, to try and come up with ways of managing that, because that obviously would destroy a reactor. These neutrons that are flying out of it, they hit the walls of the reactor at with such force that they actually damage the atomic structure, so they gradually erode the material. So if they can't come up with materials that are resistant to that erosion, they are going to have to stop these reactors every now and again to put new walls in, because...
I wonder how they, was that sort of one of those moments where someone did anybody see that crack?
Yeah.
Over there in the wall. We do this reaction now for 3 days. Somebody see that over there? Was that crack there before?
Yeah. And even sustaining it, they've managed to get these, in test environments, they've managed to get these reactors to run for maybe a minute. And then the plasma becomes a bit unstable and they can't keep it going, that kind of thing. So there's challenges there to make the reaction keep going indefinitely. But we're getting there. And one of the best signs that we're getting there is that private companies are now starting to put money, which they never did before, into this research. They wouldn't be doing that unless they felt we were near approaching the point where it might be commercially viable.
So up to this point, it's pretty much been governments
government agencies, and there are several still government labs. Like the biggest tokamak in the world is being constructed in France at the moment. There's ones in Britain. Actually, that one is closed down now, I think. There are Japan, China, the US, and the US are also belting away at the laser thing to see if they can get that to work. I mean, they've gotten it to work briefly, but if they can actually get it commercially viable, it's another matter altogether. Look, it's a very interesting technology that might give us limitless free energy someday. But that's kind of the story of fusion.
And so we've no time frame. We don't know this if they're investing money now, they're playing the long game. So it could be 10 years. We'll see some sort of we've been hiding one of these. We have one of these in a secret volcano in Hawaii.
You're after touching on one of the great jokes in physics there. I mean, for the last 50 years, fusion has been 10 years away.
Well, hopefully it is only 10 years away, because it does sound like the panacea for all our problems.
If we can get it, but it's also for our civilization, it'd be a remarkable achievement that we have actually bottled a star. Well,
and the time frame. That 120 years, we didn't know what it was doing.
Yeah.
And so in 120 years, we went from, look at what's happening out there, to, ta-da, look what I made today in Science Project.
Yes, yeah.
Limitless free energy.
Pretty awesome, all right, yeah. So with that, I think probably we've had enough of the fusion science for once.
Yes, indeed. Speaking of limitless freedom, we're going to return you to yours and say goodbye from this episode of Enough with the Science.
Okay, it's goodbye from me, Senan.
It's goodbye from Joe. Thanks for listening.